compactly grouped as orbit space.
Un minuto. Ahora sí. Well, I want to say that I'm really very pleased to be here in this very special occasion in this conference in honor of Professor Camacho, who has had so many influences in I think that everybody here and much more people. And I will speak about a subject a little bit different from others in this conference. I will talk. I will report on a joint work with Jean-Jacques Leb, which deals with complex structures on compactly groups. And perhaps the first remark that one can do in this situation is that if you take a complexly group, compact and complex, then the first thing you do when you want to understand a Lie group is to look at its linear representations, and in particular, the most important, it's the joint representation. So this is the derivative of the conjugation of the action of the group onto itself, and it gives a map into the automorphism of the Lie algebra of K. And since this comes from conjugation, the center of this, the kernel of this map is exactly the center of the group. In case the group is complex, what you have is a map which is also holomorphic. Everything is complex, this is holomorphic, and takes values in something which is contained in C and dimension of K square. And since the K is compact, this map is constant. So this means that K is abelian. K is abelian. So it's a complex torus. So not very interesting. K is abelian and particular killer. Quite surprising and very old result is the following theorem by Samuelson, which states that each compact group admits a left invariant complex structure. Yes, even dimension, yes. Even dimension. And this result is interesting because it provides a family, one of the very few families which are now, until now, of examples of non-Kähler manifolds, compact non-Kähler manifolds. So in this situation, K, if it is compact and has even dimension, it admits a left invariant complex structure. Unless it is already abelian, K is not Kähler. K is not Kähler.
That's an integrable complex structure?
Yes, integrable complex structure, yes. And so our motivation was to understand complex structures on such manifolds because they are not Kähler. And I will explain more properly this interest in a few minutes, but before perhaps I give an idea of why this is true. Why this is true. So the ideas came to Borel, and what one has to know is that when you have a compact Lie group, there is a maximal torus. A maximal torus means an abelian closed subgroup, which is maximal in the obvious sense, and this always exists because you take one parameter subgroup, you take its adherents, and this is compact and abelian. And you take the maximal one, and you can construct, in fact, a lot of maximal torus, but all of them are conjugated. I will suppose that we have fixed one of them, and another thing that you can do is to complexify K. So there exists a complex, now a complex non-compact group, complex group, which is the complexification of K. This can be done in several ways, and perhaps the best is to consider a faithful linear representation into the complex linear group. This always exists. And then you take G to be the Zariski closure of K. So and in particular, what you obtain is a complex Lie group whose Lie algebra is the direct sum of the Lie algebra of K plus E times the imaginary part, which is again the Lie algebra of K. This means that K is totally real inside G. So there is no complex structure until now. And the third thing you have to consider is a Borel subgroup. A Borel subgroup of G is a maximal solvable subgroup. Solvable subgroup of J, of G. Well, I give perhaps an example. The most typical example we can consider is SUN. This is the group of matrices which verify this and this. This is equal 1. And one can take as a torus, for instance, the diagonal matrices theta 1, theta n, 0, of determinant 1, and as a Borel subgroup that one can always take in such a way that it contains this maximal torus, one can take B to be the upper triangular matrices. So you have here zeta 1, zeta n, something here 0. This is a solvable group which contains T, and the claim is the following. Which is due to Borel. Is that so Borel proves that K over T is exactly the same thing as G over B. G over B. This is a complex manifold. In fact, in this example, if you look at this example, you take the complexification. I have not seen already what is G. You can construct G in this way. Take as a representation of K the obvious representation on Cn. This is a real Lie group defined by real and complex conditions. So you erase the real conditions and you get the complexification. The complexification is just SL and C. So if you take the quotient of SL and C by this subgroup, you see that SL acts on the flux of Cn, and B fixes a specific flag. So this is a flag manifold. And this is general. This is a projective manifold. Okay. Why this is true? I do not give the proof, but I can indicate the reason again. And this is based in, if you want, it was our decomposition of G. When for the Lie algebra. For the Lie algebra, you can decompose G as a direct sum of the Lie algebra of K plus an abelian algebra, this is abelian, plus an nilpotent subalgebra. Nilpotent subalgebra. In the example, N corresponds, in the example, N is the Lie algebra of unipotent matrices. The algebra of, in the example, unipotent matrices means those elements of B which have ones on the diagonal. So you have this. You also have that the Lie algebra of T is exactly I times A, and in particular the Lie algebra of B is, you see, the Lie algebra of B is N plus A, this belongs to B again, plus an extra term which is contained in K. This is this one plus N. And when you take the quotient by B, or the Lie algebra of B, you kill this term, and you still kill the Lie algebra corresponding to T. And from the Lie algebra point of view, this is clear. Huh? Okay. And the proof of Samuelson's theorem is based in first this construction, and what he does then is to look at this quotient, or this vibration better, with something in this form. This is a projective manifold. This is a projective manifold. This is a torus. If K is of even dimension T also, and what he does is to consider a linear complex manifold on T in such a way that K becomes complex. And this uses strongly the structure of the Lie algebra of K. Okay. So in this way, he obtains this family of non-Kähler manifolds, and these manifolds possess vector fields, but I don't think that they are pseudo parallelizable. I don't think so. Well, our motivation was to understand this construction and eventually construct new complex structures, non-invariant, in the spirit of a conjecture by Bogomolov that I want to explain here. So there is a very easy way to construct a complex structure, which is the following. If you have a X complex space, and you have a foliation, holomorphic foliation, and you have a real manifold embedded in X, real, in such a way that is transverse to F, and if the codimension of F, M, codimension of M is exactly the dimension of F, then you get a complex structure on M. So it induces a complex structure on M. So you have the foliation, you have your manifold here, which is really embedded here, and the normal coordinates provide the complex atlas on your manifold. So the conjecture says that this is true for each complex manifold, but taking X to be an algebraic space and F an algebraic foliation. But this is only a conjecture, or a question better. And what we wanted to understand was this situation in the very specific case of compact groups. So the question is it possible to look at these compact groups as transverse to some kind of algebraic foliation, or better, can we view them as orbit spaces for some kind of algebraic foliation? Okay, so I will. What I want to do is to explain the construction, but before perhaps I can concentrate to a very, very specific example. So let me speak about the concrete example. So the example is very easy. I take as a compact group the first interesting group in this list of the previous examples is SU3. This is particularly easy because 3 has a geometrical meaning, and in this case, notice that the dimension of K is, you have, this is, the dimension of K is 8. So you have 9 real conditions and an extra real condition. So this gives you dimension. In general, the dimension of SUN is n squared minus 1. So this gives you 8 here. And you can describe as above the interesting subgroups. The torus, as a torus group, you can take the diagonal A theta 1. Theta 1 minus theta 2 plus theta 2 minus I theta 2. As a Borel group, as before, you can take, sorry, let me describe just the unipotent part. 1, something here, 0. And of course, G is complexification. And finally, I will use the total group. The total group means the complexification of these complex torus, real complex torus. So this is zeta 1, zeta 2, zeta 3. Now we have 0 here, and the condition is that the product of zeta 1, zeta 2, and zeta 3 is 1. Okay. So this is isomorphic to C star square. C star square. Very good. And now we have to construct a space, a foliation, and we have to construct the algebraic space. So this is the foliation and embedding. And for this, we consider a representation. All the times we consider representations. The representation we consider here is the following one. Take C3 onto itself. Which is the following. We take here the natural action, and here this one. Transpose, sorry. And we consider this subset of C3 times T3, or better, we remove the origins. We remove the origins. We consider the quadric, or not exactly the quadric because the origins are removed, which is xy. So this is the scalar product of these two vectors, the complex scalar product. Okay, then it's easy to verify that C is the orbit of this action. Taking as a base point is it correct? Sorry, 0. The orbit of the action of this point. You take, so the points here, 1, 0, 0, 0, 0, 1. And when you consider, clearly this is a point in C, in this quadric, and this representation has been taken just to assure that the orbit of this point is inside C. And the isotropy subgroup, is exactly, so you have to fix this vector. So this gives to you 1, 0, 0 here. And its transpose inverse has to fix A3. This gives to you 1, 0. Since this is of determinant 1, you have something in N. So the isotropy subgroup is exactly, unitary. Unitary matrix. So this means that this representation provides you an embedding so this gives you an embedding of GSL3 C times the unipotent matrices inside C, which is here. And so you have the space. The space is this one. This is well, this is not exactly an algebraic variety. You take its closure, define it by the same equation. So the space will be the closure, which is an algebraic variety, a fine variety. So you need the embedding of the compact group. This is clear, and this can be seen explicitly. The compact group is SU3. And afterwards, you will need to describe the foliation. And first of all, you can see that this is exactly this intersection. The unit sphere here, which is S5, and the unit sphere here. Why? Because SU3 has a geometrical meaning. These are the orthonormal frames with respect to their meeting metric. So you have something here, two vectors which are orthogonal with respect to the complex scalar product. They become orthogonal if you conjugate one of them. And then, since they are orthogonal, and of length 1, you can just complete these taking the wedge product, and this gives to you an identification. Okay, so you take this group inside, and finally, what is the foliation? Well, since we are already inside something in particular, we have an ambient space, we can look for instance, vector fields which are tangent to C, and eventually which are transverse to K. So in principle, one takes lambda 1, x1 plus lambda 2, x2. So the easiest example you can imagine, and same thing with coordinates y. And you ask to this vector field to be tangent to C. Tangent to C. So this is easy. The condition is if you compute the derivative with respect to this vector field of this equation which defines the quadric, the condition you obtain is that the sum of lambda 1 plus mu 1 must be a constant, which is the same for each index. 1, 2, and 3. So you just have 4 degrees of freedom. So vector fields which are tangent are those ones. And what you can say is that if you can assure that the flow of this vector field is in this picture. So you have C here, you have eventually K, SU3, and you have this flow which is tangent to C. If this was transverse to this compact group, you would obtain a complex structure. Okay, but this is so there is a condition that I don't want to speak about right now. I want just to change a little bit this construction in such a way that then the general picture is almost exactly the same. For this, I write this vector field in a much more complicated way. This is the following. This is the first coefficient. I don't write everything. I just write the coefficients, alpha plus beta plus b, minus beta minus a, minus beta plus a plus b, minus beta minus b. It's the same. You have 4 degrees of freedom, and I have written this in this way because you can consider the flow, the following flow. Phi of G. G is an element of the Lie group, the complex Lie group, which is exactly the exponential of Tx times G times exponential of Ty, where X is the matrix, X is the matrix A, B. So this is in the Lie algebra of B, minus A minus B, and Y is something similar, alpha beta minus alpha minus beta. This is a flow in G. This gives to you a vector field in G, and the point is that when you consider the action, it induces a flow on the quotient, on G over U. And why? Because unipotent matrices commute with diagonal matrices. It's just that. So you have a flow on C. And this flow is exactly this one. Is exactly this one. So there is a transversality condition that I don't speak about right now, and if it is fulfilled, we will obtain the complex structure. One remark is that one can check by hand that left invariant complex structures in this example are just those corresponding to this action when x is 0. Correspond to so most of the structure are not left invariant. Okay. Well, what is the general condition? The general construction. The general construction is exactly the same. Is almost exactly the same. Huh? You just erase SU3, SL3, everything which is concrete, and what you obtain is the general picture. So I just recall here the what we are considering. We take K to be semi-simple. This is an hypothesis. We take because in the following the representations of K will be especially important, and for semi-simple groups these are very well understood, and everything is easier. But in fact it's general. I recall that if you take a compact group has an algebra which is the direct sum of a semi-simple algebra plus an abelian algebra. So this means that up to a finite cover, a compact group is a product of a semi-simple one times an abelian one. So this is a slight simplification, but makes things much more easy. Okay, so as above we have its complexification, the Borel subgroup, the toral subgroup. I recall that this is just the complexification of the torus group. We have fixed it, and in that case, I recall that this is isomorphic to C star to a power, and since we have assumed that the dimension of K is even, this has even dimension also, and say 2R. And the only point to say here is that there is an action of H, but not only H, but H times H, which is just C star for R on the space you can imagine. The space you can imagine now is abstract. It's the homogeneous space you obtain in this way, where you are unipotent. This is Borel subgroup and unipotent. Okay, this is the space. Now we have to consider also the embedding and the foliation. So the embedding is, we have no nice picture as above, but the construction is also natural. The embedding is just consider K inside G and project, okay, over U. This gives you an embedding. This is an embedding. You look at the Iwasawa decomposition again, and shows that this is an embedding. And now, what is the action or the foliation? You take any foliation is induced by a morphism from CR inside C star for R. This is h times h. As above, if this is well, this will give you a complex structure because the existence of this action. I have to say that this action is described as follows. We have on C, which is G over U, there is a left action. So there exists a left action. Of G and therefore of H. And also there exists a right action. Because when you take an element of G, or a class better, and you multiply by on the right by an element of H, this is the same thing as this one because H is in the normal, B is the normalizer of U, and H is contained inside, exactly as above. So the foliation comes by taking any embedding of CR inside this group and taking this action, and you have of course two questions. Question one is to describe or formulate in some way the transversality condition. What is the transversality condition? And the second one, to look at the complex structures obtained, and in particular to see if there are other, if there are structures which are not left invariant. There exists structure non-invariant left structures. Well, the question one can be answered, but it's a little bit technical because it makes appear the action of the Bell group of G. And there is also an answer to question two, and is this one that I can explain a little bit. So we look at the picture we have. There is an algebraic manifold, which is this quotient. And inside you have K, and in fact the remark here is that the orbits of CR meet K, which is inside, exactly once. If it is transversal also, always. So what you have is an identification of this transversal manifold to the orbit space of the foliation, and the fiber is CR. And because of the construction, this is a CR principal bundle. CR principal bundle. You have a lot of structure. Okay, and the problem now is to see how different are the different how varied the complex structure when you change this vector field or this family of vector fields. Okay. So the answer is based in the following result. Is the following. There exists a linear representation of G with a suitable n in such a way that C contained here. Until now, I am not saying what is C, but because of the construction, since G is obtained as an algebraic object, G is an algebraic group, and therefore, if we take the Zariski closure of this coincides to the topological closure, and this is a fine algebraic variety. Okay. This is not very difficult. You take, since the group is semi-simple, you take fundamental representations, you take their direct sum, and you can obtain this easily. But you can, what is important here are the conclusion. Using this particular choice of the representation, what you can obtain is that functions over C, holomorphic functions over C, coincide with holomorphic functions over its closure. If this was, if C was non-singular, this should be some kind of Artok's theorem, and you would need a big codimension of the singular set. But in general, you need a little bit more, so because it's an singular space. But there is a theorem by Su which gives a relation between the cohomology groups of an analytic space with values in a covariant sheaf when you remove some analytic subset. And this is true if the codimension of A is big enough. But to be precise, we need a little bit more. We need that A has sufficient homological codimension, what is called the depth. So you need to assure that the depth of the singular locus is big enough. And here the question is that as you know very precisely what are the representations, you can compute explicitly and to assure that this is true. This is true for this one and for this one. And since this is an algebraic variety, this is 0. Okay. And now, when you have this, you can conclude by standard arguments, the corollary, that generically or almost the complex structure are not invariant. And well, I just give briefly the idea of the proof of this corollary. The idea for R equal 1, which is the simple case. In this case, you have to put C inside RS1. So you have to put here in C star 4. R is so you have two vector fields here. So this is C star square to star square. You have T to exponential T x exponential of Ty, and the first point is to see that if you consider this vibration, This is over K, and here you have just a copy of C, just a vector field. This is a C principal bundle, and you can identify holomorphic functions here, holomorphic functions on K. When you take their pullback by P, this is exactly the holomorphic functions on C, which are invariant by the action of C. This is the functions which are transverse to the foliation. And the claim here, the first claim, is that each H1 of OK, so K with values OK, is the same to this one. Sorry, here C, because this space contracts on K topologically, and this is C. This is exactly C. To compute this, you use along exact sequence associated to this one. This is the lead derivative with respect to the vector field. These are functions which are invariant, and the associated long exact sequence gives you this one, H1 with values in sorry. Sorry, I have written this perhaps in the inverse sense. These are the invariant. Okay, now it's correct. And we already know that this group is 0, and you can compute that the co-kernel here is C, so this gives the result. And this is the first point. The second point is that sub-C principal bundles over K are the same thing as elements of H1 with values in OK, and this is C. It is well known that when you take here O star, you get C star principal bundles or circle bundles. And you take here, you have something additive, and these are C principal bundles. And third, the bundle defined by C is not trivial. It's not trivial because if it was trivial, this would give you it would have a section, and if you have a section, since C is contained in Cn, and this would give to you a holomorphic map inside Cn, and it would be constant. So it cannot be trivial, and all non-trivial elements, all other non-trivial elements here are given by the same vector field, but multiplied by a constant different from 0. So you just change the time, and this gives to you all the elements. And finally you conclude, because in this situation if you have an identification among these quotients of this type, the two quotients of this type, if you have something here which is bialomorphic, this map also is defined in cohomology, which gives to you a correspondence from the total space of these principal bundles. So you have a principal bundle here which is not trivial, so the total space is necessarily C. Its pullback by F is also non-trivial, so the total space is also C, and you have a pullback here. And now you can finally see that generically F tilde is linear, so you can do explicit computations and conclude that the only way generically F tilde is linear if there are not rational relations between the eigenvalues of the two vector fields, and you can compute explicitly that in this case the manifolds are isomorphic if and only if the maps are conjugated. So in general they are not invariant. And I think that we'll stop here. Thank you for your attention.